So when you have a beaker, when you have a beaker full of water, we know that you will have water molecules here and then water molecules everywhere. So let's actually focus on the water molecules around here. What happens at near to this area? It means something will happen somewhere here. This line, at the surface of the water, and it's very difficult for me to keep on drawing like this. So what I will do now is I will try to replicate this line. I put it around here. So actually the line supposed to be somewhere here. I'm going to just replicate the line over there. Now what happens is, at a normal situation, the water molecules, they do not actually simply just change into gas and evaporate and so on. So what happens is they will have some sort of what we call as equilibrium. Under equilibrium, there will be a constant change of these water molecules, to change into gas, and then they will actually come back down as liquid again. Just imagine, just imagine if you have a container, and it is closed. It is closed. So let's say the water molecules change into gas. When they go up, what happens? They cannot go anymore. They will lose their energy, and then they will change from gas. They will lose their energy, means they will change into liquid. They will condense, and then they will form droplets of water, and then they fall back again. They will fall back again. Why? Because they cannot escape, because of the physical barrier that you have over here. Yeah, Jeffrey, you can go. You have a physical barrier over there, that will actually prevent the gas from escaping. In this case, if you look at this, the physical barrier that we are talking about, even though the beaker is not closed, the physical barrier that we are going to talk about over here is the air itself. The air itself will actually exert a pressure. So this pressure exerted by the air towards the water molecules, it means it's supposed to be more towards here. I'm drawing way up so that you can actually see. So what happens over here, the pressure exerted by the air will keep the water molecules in the beaker. They will keep it in the beaker. So it means it will replicate something similar to this. So this is called as atmospheric pressure. Now, whenever you have atmospheric pressure, just imagine now this is a physical barrier, but this is going to be some sort of a virtual barrier. Similar, if let's say now I'm going to ignore about this, I'm putting it way on top so that I can show you clearly. So what happens, when water molecules, they let's say change into gas, when they go up, because of the atmospheric pressure, they will change back into liquid. They will lose their energy. They will change into liquid, and then they will come and drop down. It means that whatever that the water molecules that goes up, they will come back and drop down. So this one is called equilibrium, where water molecules, when they change into gas, they will be changing back into liquid again. So I'm going to actually draw another line over there. So whatever that is being changed into gas, they will come back again as liquid. So what happens over here is nothing, from this beaker goes out from the beaker itself. It means evaporation is not even happening. It means water molecules, they are not going to escape. It's not going to happen. So since there is nothing that is being changed, nothing is going outside of the system, we can say that the concentration, of the water is going to be constant. Concentration is constant. So this one, if we say, is it a closed system or is it going to be an open system? If you have a physical barrier, nothing goes out, nothing comes in, we say it's a closed system. Okay, it's a closed system. But here, even though there is no physical barrier, it's open. Okay, it's open. There is no cover or lid trying to actually prevent the water from going out. But okay, you have to consider about the air pressure or the atmospheric pressure. So this atmospheric pressure prevents anything from going out. Nothing is coming inside, no water molecules coming inside. So this is also a closed system. Okay, just imagine, even though there is no physical lid or cover, okay, this is still a closed system. Okay, because nothing goes out, nothing comes in. Okay, we will learn more under equilibrium for this. Now, this is still under equilibrium. Now, what happens? Okay, what happens? The moment when you have, okay, this gas, okay, gas going out, okay, it means that they are, okay, if let's say they are going out, so imagine I'm actually using another pen over here. They are going against the atmospheric pressure. Let's say this is a water in form of gas. They are trying to overcome, okay, the atmospheric pressure, but because they are four lines, okay, because there are four lines trying to hold them together, the atmospheric pressure is greater than the pressure exerted by this gas. Okay, the pressure exerted by this gas is called vapor pressure, VP. Okay, vapor pressure. So I'm going to actually put it over here. What is vapor pressure? Vapor pressure is the pressure exerted, okay, pressure exerted by vapor in equilibrium. Okay, it's a pressure exerted by the vapor in equilibrium. So now they are trying to exert the pressure, so they cannot go out. Now what happens, okay, under certain situation when they have enough energy or enough vapor pressure to overcome, okay, the atmospheric pressure, then evaporation and boiling can happen. So what happens is, let's say under the hot sun, okay, so if let's say under hot sun, so they will gain energy. Okay, this particle, okay, they will actually gain energy. Okay, they will gain enough energy so that they can actually overcome this particular atmospheric pressure. So what happens, since they actually have enough energy, they can actually go outside. Okay, but not all of the particles can have enough energy to overcome the atmospheric pressure. That's the reason why evaporation happens only at the surface of the liquid. Okay, because only then they will have enough energy and then they can escape. Maybe this one, the energy is not enough. The energy is not enough. So the one that is actually at the top of the surface of the water will be the one that has more energy. And once they have enough energy or enough kinetic energy to escape or break the bonds between other water molecules, okay, they can actually go out and they can overcome the atmospheric pressure. They can go out and then they can be evaporated. But do remember, not all molecules are capable to do that. So what happens if, let's say, you provide heat? Now, if you heat up, okay, there will be more molecules of water will actually start to rearrange themselves at the surface. Okay, so what happens, okay, when you heat up, okay, there will be more water molecules that start to rise. Okay, they start to rise, and there will be more water molecules trying to exert the vapor pressure. So the vapor pressure will increase now. So now the more temperature, okay, the vapor pressure will be more. The vapor pressure will be more until to an extent, if you have 1, 2, 3, 4 atmospheric pressure, you can see the vapor pressure is also having 4. The moment the vapor pressure is equal to the atmospheric pressure, okay, what happens is the barrier that is holding them, will be broken. Once the barrier is broken, there's nothing, okay, there's nothing that can prevent them from going out. Okay, the barrier is broken. Okay, so it's not being reflected in my screen over here, I think, because slow connection. Okay, anyway, what happens, there is no barrier. Okay, the barrier will be gone. So you can see now, okay, on your screen, there is no barrier, no dotted line. So what happens is all the water molecules now have equal opportunity to just simply escape to the environment. They can escape to the environment. They can escape to the environment. So all of them will have enough energy to escape to the environment. So that condition is what we call as boiling point. Okay, boiling point is the temperature. Okay, it's a temperature where, okay, the vapor pressure, the VP, okay, I wrote it as VP. Okay, hold on, it's not actually reflecting as well. Maybe my connection is quite weak. I'll try to share it again. Okay, I'll stop screen sharing. Okay, let's see. The connection is not so good. It's not shown. Hold on, guys. Okay, the connection is quite weak. Okay, let me actually restart the Zoom in my iPad. Okay, just give me a moment. Okay, you can see now. Okay, anyway, so if we continue, okay, the boiling point, okay, is going to be the temperature when your vapor pressure, okay, the pressure exerted by the vapor in equilibrium is the same as atmospheric pressure. Okay, it's the same as atmospheric pressure. So once you have the same vapor pressure as the atmospheric pressure, it means that nothing, okay, previously the water molecules are being held down by the atmospheric pressure. But now all this vapor pressure, they can actually overcome the atmospheric pressure. It means that now the whatever barrier that exists between them that holds the water molecules into the beaker is no more. Okay, so they can actually simply escape to the environment. Okay, they can simply escape to the environment if they have enough energy. So now it's not the way pressure holding them down. The only thing that is holding them down is the energy. So Mr. Gopi, why when I boil something, okay, if let's say there is no physical barrier, why suddenly when they reach at 100 degrees Celsius, which is going to be the boiling point, why suddenly at that instant, the water suddenly disappear completely? Why I don't see that? Okay, why it still takes time for the boiling to take place? Okay, to answer that, okay, now it will not actually, since the physical barrier is gone, then everything can just simply go. Okay, it also depends on the energy. So some of them, okay, they are still boiling. So not all of them completely boil yet. So not all the water molecules have enough energy, okay, to get the enough energy to break the bonds between each other, because each of them are still having intermolecular forces of attraction. So they still need to break these forces of attraction. Okay, once they break free, they do not have anything that is holding them down anymore. They can just simply go. So it means that's why at the moment it reach 100 degrees Celsius, yeah, it will still take time for all of these to completely disappear. Okay, so once all of them, okay, but just to say that what happens during boiling point, it means there is no barrier which is going to be the atmospheric pressure trying to hold them down or trying to make them stay. Okay, so it means that now it's like it's freedom for you. Okay, freedom for the gas molecules to go anywhere that they like, but you must have enough energy to break away from each other so they can go. So that is actually what we call as boiling point. Okay, now if you look at let's say we try to apply this concept into day-to-day life. Okay, so I've drawn a diagram over here. Okay, let's say we have two people, okay, staying in around a mountain area. Okay, so this one is the sea. Okay, so you can see a great white shark over there. Okay, anyway, okay, you see someone. Okay, let's put someone staying here. Maybe Arwen is staying here. Okay, and then let's say Po Yiwen is actually staying here. Okay, so both of you are staying, but at different altitudes. Okay, at different altitudes, and both of you actually try to wash your BBS uniform. Okay, try to wash your BBS uniform, and let's say, okay, at the same time, Sunday, okay, the next day is school, and then you wash it on Sunday. Still a lot of rain. Okay, it's still the weather is not so good nowadays. Okay, every day is raining. So now anyway, let's actually compare Yiwen and Arwen. They didn't prepare earlier. They washed their clothes at night time. Okay, and then try to dry the clothes. Okay, so can someone tell me who will be having the probability of the clothes will not be dry the next following day? Sharon? Who do you think the clothes will not dry easily?
R1.
Why? If Arwen, why?
It's lower. Like,
Lower point.
yeah.
Uh, Lower point means they are closer to the sea. That is what you mean?
Yes.
Okay. Actually, when you look over here, okay, let's actually forget about these houses. Let's focus on this mountain area. Okay, let's focus on the mountain area. Uh, all these parts are covered by air. Okay, all these parts are covered by air. It means that, okay, the higher, the lower place that you are going to be compressed by a lot of air. Correct? Do you agree? So all these are air. Okay, you are going to be compressed or going to experience a lot of air around you. Now, the moment, okay, when you go slightly higher, all the air below you will not take any effect towards you. So now you only have less air surrounding you. I want you to understand this situation first. Okay, the higher altitude that you have, okay, you will have less air surrounding you because all this air, okay, they are not going to take they will not push you. So if I actually put it in let's say, I think much more easier if you can imagine, okay, in let's say under the water. Okay, it's much more easier to explain if you are under the water. Okay, let's say you are under the water. Okay, you get stuck over here, and then you get stuck over here. Okay, who will die first? Michelle? A or B?
B,
Why?
because the pressure is more.
Okay,
Because it's
ignore the great white shark. Yeah, so basically you are going to talk about the pressure. Okay, let's talk about the pressure. The pressure when you are at the bottom, okay, the pressure is going to be high. We are talking about the pressure of the water. Okay, there will be more water surrounding you. When you are on top, less water surrounding you. So pressure is less. So if you use the same concept over here, if you're staying here, there will be more atmospheric pressure because a lot of air. If you're staying here, there will be less air, okay, because all the air below is not going to influence you, only the air at the top, okay. So because of the gravity, oxygen also being pulled more towards the ground, okay, or all the other air will be more towards here compared to here, so less air, okay. So what you can say over here is the atmospheric pressure, okay, is lower. Atmospheric pressure is lower here. Atmospheric pressure here is going to be higher. Pressure is higher. Now coming back to E1 and R1. Okay. So now what happens is if I represent the atmospheric pressure using arrows, okay, there are 4 atmospheric pressure, for example, here. E1 only have, okay, 2 atmospheric pressure over here, lower, to show that the atmospheric pressure is lower. So when you evaporate, okay, when you try to let's say the water from your clothes, they want to go out, okay, they will exert some sort of a vapor pressure, okay, they will actually exert the vapor pressure. So the vapor pressure that they need to exert, okay, for E1 will be only 2 lines over here. But for R1, there should be more. And in order to reach that more lines over there for R1, there should be much more heat. Okay, imagine the sun is constant. The amount of heat that E1 and R1 is getting is still the same. So with less heat, E1, okay, will be able to actually dry his clothes faster compared to R1. Can you understand this? Because, okay, the vapor pressure, okay, that even clothes or the water in even clothes, okay, they will become equal to the atmospheric pressure at much more lower heat or lower energy. So it means that, okay, it means that Mr. Gopi, are you telling that, okay, if even stay way higher up into the mountain and then R1 is staying way closer to the sea, if she boils water, if we boil water, if even boil water, am I saying the boiling, if I boil water, R1 is going to be 100 degrees Celsius. Water is going to boil at 100 degrees Celsius. Even, so let's ask even. Even, do you think that when you boil water at the top of the mountain, is it going to be still 100 degrees Celsius?
Yes.
No, it's not going to be 100 degrees Celsius anymore. Okay, because, okay, you have to actually understand the concept of boiling point. Okay, boiling point is going to be when the vapor pressure is the same as atmospheric pressure, then it's boiling point. Okay, so 100 degrees Celsius is going to be the boiling point, okay, at a pressure, at a particular pressure. Okay, 100 degrees Celsius, it happens at 101 kilopascal. This one in I think in most of the situation, this is the standard condition. Yeah, 101 kilopascal. But now the pressure is different. When the pressure is different, your boiling point is going to be different as well. Okay, your atmospheric pressure is lower, so it's much more easier for even, okay, to boil water. It means the even might actually will be able to boil the water at 80 degrees Celsius. It's not magic. Okay, this one is a simple knowledge, okay, using the atmospheric pressure. It means boiling point, even though we say for water is 100 degrees Celsius, boiling point can be different at different condition. In this case, I'm talking about atmospheric pressure. That's why the reason why chemists or any kind of let's say experiments when we do, we say standard condition and pressure. Why it must be done as standard condition and pressure? Okay, because if we are doing it in Indonesia, so maybe we are doing it in 25 degrees Celsius and we are doing it at 1 atmospheric pressure. But if let's say another scientist or another chemist wants to do the same experiment on top of let's say Mount Everest, okay, will he be able to replicate the same results? He won't be able to replicate the same results because the temperature will be different than 25, the pressure will be different than 1. Okay, so what they need to do, okay, it means they need to build a lab, okay, which can actually give you the same situation as standard condition in order to get the same results. Okay, that's why we always say a standard condition must be applied. So here, okay, that's why sometimes when we do experiments, our experiment will not be the same as everyone everywhere. Okay, it will not be the same because of different conditions. Okay, so here, okay, that's why, okay, if even trying to dry the clothes, okay, most likely it will dry much more faster, assuming, okay, they are receiving the same number of heat. Okay, so R1 is receiving the same number of heat. Okay, E1 is receiving the same number of heat, but E1's clothes will be able to dry faster, okay, because they are able to reach the atmospheric pressure much more earlier than R1. Okay, so if we actually try to apply this concept in bio, okay, how do we apply this concept in bio? Same concept, okay, I will just discuss because we already tried to explain this. If let's say, okay, you are staying here, R1 is staying here, and then E1 is staying here, who will be having difficulties in breathing, E1 or R1? R1, can you actually answer this? Who will be having difficulties in breathing, E1 or R1?
Even.
Even will have difficulty in breathing. Why? Okay, that's correct. Okay, even will have difficulty in breathing. Okay, why? Because whenever we want to breathe, okay, our lung, okay, I think let's not go into the anatomy part and so on, okay, the diaphragm and so on. But anyway, our body, okay, our body must have lower pressure. Okay, our lung must have a lower pressure so that, okay, the pressure outside is higher, okay, the air. So air always travel from higher pressure to lower pressure. I think a simple concept of physics. Okay, so pressure will move from higher pressure to lower pressure, so they will enter the lung. Okay, so what happens over here? I think for R1 is still like normal. Pressure outside is higher, lung pressure is like normal, lower, so they will enter without any problem. But the problem over here is as you go to the higher altitude, okay, what happens is the atmospheric pressure will drop. So it means the atmospheric pressure will be slightly higher only. It will drop. So it will not be able to enter, or it will be something like similar to your pressure of the lung. The higher you go, okay, the pressure will be almost similar to your lung pressure will be the same as the atmospheric pressure. So what happens, the air from outside, they will have difficulty to enter your lung. Okay, even though there is enough air, okay, but it's difficult to enter because of difference in pressure. Okay, so that's the reason I think if you watch movies or something, if let's say you want to climb Mount Everest, okay, if you want to climb Mount Everest, some of them when they almost coming to the summit, yeah, they have to go down. Okay, sometimes last time I always imagine, you know, the how come, okay, last time they used to send I think a team of Malaysians, 1998, a team of Malaysians tried to conquer Mount Everest. And then out of a team of 10 people, only 2 people actually went to the top. And then the remaining ones, they only have 200 meters to go to the summit, but they didn't go all the way to the top. I was wondering how come it's only 200 meters, it's so near. Why they didn't go all the way to the up? Okay, why they have to actually chicken out and actually go down? I was always thinking like that. Okay, but later when I learned, okay, it's more towards the air pressure, because I think when coming near to the summit, the air pressure is very, very low. That's why from the base camp all the way to the top, they will actually bring oxygen supply, oxygen mask. Okay, they will carry that. So they can actually use it when they go to the top. So what happens, some of them will have problems, okay, like for example, difficulty in breathing. They will utilize the oxygen around here. So by the time they come over here, when they try to calculate the oxygen that they have, it will not be enough for them to last until they go to the summit, even though it's only 200 meter. Okay, so they just stop over there and then go down. So the thing is, okay, it is impossible to actually go all the way to the top without a gas mask for Everest. Okay, so because some of them, they actually still need to use the oxygen during the climbing. Okay, so that's the problem why not everyone can manage to reach to the top, to the summit. Okay, some of them even they stop over here, maybe because of other problems, frostbite and so on. Okay, a lot of other problems. Okay, but again, if you're wondering why they cannot reach to the top, okay, that's the reason. Okay, because at the top, okay, the pressure is too low. Okay, so they cannot the lung cannot generate lower pressure until it cannot actually enter the body, even though there's oxygen around. Okay, the oxygen cannot enter the body, so you still need to actually wear the gas mask and actually go to the top. Okay, yeah, Jeffrey can. So that is actually the explanation. Okay, when you look at the vapor pressure. Okay, I've explained about vapor pressure. I've explained about the atmospheric pressure, boiling point. I even actually try to explain using some kind of a daily applications, okay, related to vapor pressure and atmospheric pressure. Okay, so what are the things that you must know? Okay, the things that you must know is, okay, you need to know what is vapor pressure. Vapor pressure is the pressure exerted, okay, by the vapor in equilibrium. Okay, by the vapor in equilibrium. So when the temperature goes up, what happens to the vapor pressure? Vapor pressure also will go up. At certain temperature, okay, which is going to be the boiling point, okay, which is 100 degrees, for example, for water. At certain temperature, the vapor pressure will be the same as your atmospheric pressure. So once you actually get that, so that is the time where there is no barrier, okay, that holds the water molecules to stick or to stay at the surface. So that's the time that the water molecules can break free. Okay, there is no need to consider about equilibrium anymore. They start to break free and then they just move out. Okay, so the concentration of water will not be constant anymore because they are going to go out. Okay, so that is going to be the atmospheric pressure, vapor pressure equals to atmospheric pressure. That is going to be boiling point. Application wise, okay, I told you, okay, when you go at higher altitude, okay, you will have less air pressure, so you can actually reach the vapor pressure can reach the atmospheric pressure much more faster at higher altitude. Okay, so even though you have some kind of advantage over there, but the higher you go, you will have problem with breathing. Okay, that's going to be the problem as well. Okay, so I'll open now for questions.